Okay, good morning to you. Today,
Good morning, Mr.
Today we are going to see the two most important theorems that can be applied to find the zeros of a polynomial. These are location theorem, which is primarily used to locate the irrational zeros of a given polynomial between consecutive integer. And the second one is the rational root test theorem, which is used to find the rational zeros of a given polynomial. Actually, if a polynomial is defined in the set of real number, then because real number is the union of rational and irrational numbers, therefore the zeros of a polynomial are categorized into two as irrational and rational zeros. And for irrational zeros, you have to remember location theorem. You have to remember and use the content of location theorem to locate the irrational zeros of a given polynomial between consecutive integers. And if a given polynomial has any irrational zeros, then by using the rational root test theorem, you can find those zeros of a given polynomial. Now let us see the content of each of these theorems. That means how we can use them to find to locate the irrational zeros of a polynomial and to find the rational zeros of a polynomial. We begin our discussion with location theorem. Let A and B real numbers such that A is less than B. Two real numbers are given, they are distinct. That means B is greater than A or A is the smaller of the two. If f is a polynomial function such that f of A and f of B have opposite signs, that means f of A positive, f of B negative, or f of A negative, f of B positive, then there is at least one zero of f between these two consecutive integers. So location theorem guarantees the existence of an irrational zero, and it is, or the irrational zero of a polynomial is obtained where the polynomial changes its sign between consecutive integers in our context. Actually, the theorem generalizes. It is used for in the set of real number, but in our case, we consider integers, and the given polynomial changes its sign from positive to negative or from negative, then there exists at least the polynomial. Let us see this with numerical examples. So the first example is, for each of the following polynomial functions, construct a table of values and use the location theorem to locate the zeros of f between successive integers. A, f of x is equal to 3x cubed plus x squared plus x minus 2. B, f of x is equal to x to the power of 4 minus 6x cubed plus x squared plus 12x minus 6. And C, 4x to the power of 4, 7x minus 15. Now, most often, when we are interested to locate the irrational zeros of a polynomial between consecutive integers, we prepare a table. So, to construct this table, often we use the 5 integers minus 2, minus 1, 0, 1, and 2. And we evaluate the given polynomial at these integers, and we will observe. For example, the first one, its leading coefficient is positive. If its leading coefficient is positive, a polynomial, even or odd degree, it is rising on the right extreme. On the right extreme means as the value of x is increasing from 0 to 1, 1, 2, 2, 2, 3, 3, 2, 4, etc. Then its graph is rising or the value of f of x is rising. So once the value of f of x is positive on the right extreme, there is no chance for f of x to come back to assume a value of negative and then positive. So we will evaluate this polynomial f of x at these 5 integers. So the result is as follows. The result is for the first polynomial x minus 2 minus 1 0 1 and 2, and f of x is 3x cube. F of x, it is equal to 3x cube plus x squared plus x minus 2. I think it is this one. 3x cube x squared plus x minus 2. So when the value of x is minus 2, what is the corresponding value of f of x? Here you will substitute minus 2. Minus to the power of 3 is minus 8. Minus 8 times 3 is minus 24. Minus 2 the whole square is 4. So it is minus 20. Minus 20, minus 2, minus 2. It is minus 24. If you evaluate this at minus 3, again, minus 3 cube is minus 27. Minus 27 times 3 is minus 81. Whatever the value of x squared plus x minus 2, the value of f of x is negative. So beyond minus 2, f of x remains negative or less than 0. So no need of wasting our time by evaluating f at minus 3, minus 4, minus 5, because in all these cases, the value of f of x remains negative. So what is the value of f of x when x is equal to minus 1? As we did earlier, substitute x by minus 1 and simplify. Minus 1 cube is minus 1. Minus 1 times 3 is minus 3. Minus 1 square is positive 1. So minus 3 plus 1 is minus 2. Here we have minus 1 and minus 2. It is equal to minus 3. Minus 3 minus 2 is minus 5. Then at 0, the value of f of x at x is equal to 0 is always equal to the constant term in a polynomial. So the constant term of the polynomial minus 2. So still it is negative. Now when x is equal to 1, 3 plus 1 plus 1 is 5. 5 minus 2 is 3. So it is 3 and it is positive. Now f of x at x is equal to 2. 2 cubed is 8 times 3, 24. 24 plus 4 is 28. 28 plus 2 is 26. 26 minus 2 is, it is, yep, 20, it is 24, 28. Yes, it is 28. 28 plus 2 is 30. 30 minus 2 is 28. So this is negative, 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 positive, positive. Now, f of x, if you evaluate this function f of x beyond 2, its value remains positive, so no need of wasting our time. Just think of the content of the location theorem. According to location theorem, an irrational zero of a polynomial is obtained between consecutive integers where that polynomial changes its sign. And as you can see from this table, it is between 0 and 1. F of x changes its sign from negative to positive as the value of x increases from 0 to 1. So by location theorem, at least one irrational zero of a polynomial is obtained between these two consecutive integers 0 and 1. So as can be seen from the table, f changes its sign between 0 and 1. So by the location 1. If I ask you a question, the maximum number of possible zeros of this polynomial is how many? How many zeros can this polynomial have?
3.
Yes, for a given polynomial, the maximum number of possible zeros or the maximum number of possible factors of a polynomial is always equal to its degree. So it can have 3 different zeros. But in this case, the location theorem assured us that between consecutive integers where the given polynomial changes its sign, there is at least one irrational zero. Therefore, one irrational zero of f of x is obtained between 0 and 1. Let us consider the second polynomial. F of x is equal to x to the power of 4 minus 6x cubed, x squared, 12x minus 6. Okay, let me write it here. F of x is equal to x to the power of 4 minus 6 x cubed plus x squared plus 12x minus 6. Again, let us start from the maximum number of possible zeros of this polynomial. As I said for the previous example, the maximum number of possible zeros of this polynomial is 4, which is equal to its degree. Now, let us prepare the table. And let us evaluate it at minus 2. Minus 2 to the power of 4 is 16. Minus 2 to the power of 3 is minus 8. Minus 8 times minus 6 is positive 48. 48 plus 16 is 64. Then minus 2 square is 4. It is 68. 68, but in this case, 12 times minus 2 is minus 24. Minus 24 minus 6 is minus 30. Minus 68 minus 30, it is equal to 38. And it is positive. Minus 1, this is 1, this is 6, and here we have 1. 1, 1, 6, it is 8. 8 minus 6 is 2. And here we have minus 12. 2 minus 12 is minus 10. So f of x changes its sign between minus 2 and minus 1. So one irrational zero of this polynomial is obtained between minus 2 and minus 1, where f changes its sign from positive to negative. Now, at x is equal to 0, f of x is equal to the constant term of the polynomial, which is equal to minus 6. Now, between minus 1 and 0, by location theorem, there is no irrational zero because the sign of f of x is negative. Again, at x is equal to 1, if you make the value of x 1, this is 1, this is minus 6, this is 1, this is 12. 12 plus 1 is 13, 13 plus 1 is 14, minus 6 is 12, 14 minus 12 is positive 2. Now again, between 0 and 1, f of x changes its sign from negative to positive. Another irrational zero polynomial is obtained between these two negative integers, between minus 2 and minus 1, between 0 and 1. Now, if I evaluate this polynomial at x is equal to 2, the result is minus 10. At 3, it is minus 42. At 4, minus 70. At 5, minus 46. And at 6, it is equal to 102. Now, we have obtained between minus 2 and minus 1, between 0 and 1, again between 1 and 2, because at x is equal to 1, it is positive. At x is equal to 2, its sign is changed into negative. So here we have 1, here we have 2, 3, 1 more to go, because the maximum possible number of zeros of this polynomial is 4, and the fourth zero of this polynomial is obtained between 5 and 6. As you can see from this table, f of x changes its sign from negative to positive as the value of x changes from 5 to 6. So f changes its sign between minus 2 and minus 1, 0 and 1, 1 and 2, and 5 and 6, which means it has its irrational zeros between these consecutive integers. The third example is the polynomial is 4x to the power of 4
4x the power of 4, 7x minus 50.
Zeros of this polynomial is 4, or all the possible zeros of this polynomial is less than or equal to its degree 4. So this polynomial can have at maximum 4 different zeros, or 3, or 2, or 1, or no zero. To see this, let us construct the table. Evaluate f of x at x is equal to minus 2, minus 1, 0, 1, 2, and 3. As you can see from the table, the value of f of x is 35 when x is equal to minus 2. At x is equal to minus 1, it is negative 18. So the value of f of x is changed from positive to negative between minus and minus 1. So by location theorem, the polynomial has at least one irrational zero between minus 1, minus 2, and minus 1. Then at x is equal to 1, still it is negative. At x is equal to 2, it is positive. At x is equal to 3, positive. Now beyond 3, the value of f of x is, because after some point in a polynomial, the sign of the polynomial is determined by its leading coefficient. So if its leading coefficient is positive, then maybe beyond 2, beyond 3, or beyond 1, it is depending on the nature of these coefficients. Actually, after 2, in this case, there is no chance for f of x to assume a negative value. So no need of wasting our time by evaluating f at 4, 5, etc. Let us remember the content of location theorem. Between minus 2 and minus 1, f of x changes its sign from positive to negative, between to positive. Therefore, this polynomial has at least one irrational zero between minus 2 and minus 1, another irrational zero between 1 and 2. So the correct answer for this is f changes its sign between minus 2 and minus 1, and 1 and 2, which means it has its irrational zeros between these consecutive integers. So I think location theorem is difficult to understand. It is a matter of remembering the content of its theorem in order to see where the given polynomial changes its sign as the value of x changes from a given integer to another integer. The second example is using the location theorem shows that the polynomial f of x is equal to x to the power of 5 minus 2x squared minus 1 as a zero between x is equal to 1 and x is equal to 2. Just this problem is similar to show the value of f of x at equal to 1 and f of x at x is equal to 2 is positive and negative. That means we compare the signs of f of 1 and f of 2. F of 1 is equal to minus 2. F of 2 is equal to 23. As you can see, f of 1 is a negative number, that is f of 1 is less than 0. F of 2 is a positive number and greater than 0. If you remember, location theorem states that if f of a is positive and f of b is negative, or f of a is negative and f of b is numbers, at least one irrational zero of a polynomial exists. Therefore, because f of 1 is less than 0 or negative and f of 2 is greater than 0, by location theorem, f has a zero between 1 and 2. The third example, using the location theorem,
shows that the polynomial f of x is equal to x cubed minus 5x minus 1 as a 0 between x minus 3 and x minus 2. Again, this problem is similar to f of minus 3 and f of minus 2. F changes its sign. No. Compare the sign of f of minus 1. F of minus 3 is equal to 1, which is positive. F of minus 3, it is equal to f of minus 3 is equal to minus 13. Therefore, f of minus 2 is greater than 0. F of minus 3 is less than, has at least one 0 between minus 3 and minus 2. This is all I have regarding location theorem. Let us see rational root test theorem. What is its content? It can be used. Okay, rational root test, theorem 1.5. The rational root test theorem is if the rational number p over q in its lowest terms is a 0 of the polynomial f of x, which is equal to an x to the power of n, an minus 1 x to the power of n minus 1, a1x plus a sub 0 with integer coefficients, then p must be a factor of a0 and q. And q must be a factor of an. I think rational root test theorem is better understood with examples. So let me use these examples and explain for you the content of the theorem. For each of the following polynomials, find all the possible rational zeros. First, there is one condition to apply the test of a polynomial, all the coefficients. If one of them is not a rational number, or one of them is irrational number, then we cannot use the rational root test theorem. All the coefficients of the polynomial must be integers. Unless the coefficients of a polynomial are integers, then we cannot use the rational root test theorem. So this is the first condition. If all the coefficients of a polynomial are integers, then we can use the rational root test theorem. According to the rational root test theorem, or to apply this, we only consider the leading coefficient and the constant term of a polynomial. In this case, the constant term is 4 and the leading coefficient is 3. The constant term of a polynomial is p. Its leading coefficient is q, because as you remember in the theorem, it is explained as first, list the factors of p over q in its simplest form. Now, what is the importance or how this theorem is helpful in finding the zeros of a rational number? Always before we try to solve or we try to find the zeros of a polynomial, you know that the domain of a polynomial function is a real number. Therefore, its zeros are one of these real numbers. If they exist, that means if the zero of a polynomial exists, it is among the list of real numbers or from the set of real numbers. So think of solving a problem in the set of real number and from among a set that contains fixed number of elements. It is to narrow down our finding. What are the possible solutions of a given polynomial? So for this purpose, because the constant term is represented by p, list the factors of p. The factors of p, in this context, it is 4 and list the factors of 4. They are plus or minus 1, plus or minus 2, and plus or minus 4. And the leading coefficient is 3. So it is represented by Q, and list the factors of Q. They are plus or minus 1 and plus or minus 3. Now the factors of P over Q. P over Q, don't forget to put this plus or minus sign before each of the factors of this polynomial. Then form P over Q. What is 1 over 1? It is equal to 1. So the first factor of P over Q is plus or minus 1. Then 1 over 3. Plus or minus 1 over 3. Then consider the next factor of P, that is 2. Then list the factors of P over Q whose denominator is 2. Plus or minus 2 over plus or minus 1. Or it is simply 2 over 1. We place the plus or minus sign before this factor. So plus or minus 2. Then 2 over 3. Plus or minus 2 over 3. Then the final factor of P. So by considering this, we list the factors of P over Q whose numerator is 4. So 4 over 1 is 4. Therefore, plus or minus 4. 4 over 3 plus or minus 4 over 3. Now we are not going to think solving this problem in the set of real number. If this polynomial has any rational zero, it must be among 1, 2, 3, 4, 5, 6. These 12 numbers. So the maximum possible, or in the state of real number solution ከማሰብ አሁን ያስቀመጥናቸው 1 2 3 4 5 6 12 ቁጥሮች አሉ። ዜሮዎች ካሉት 12 ጊዜ መሞከር ነው የሚሆነው ማክሲመም ልፋታችን ነው። So we list out all these 12 numbers. So most often we try to find the zeros of this polynomial from the simplest factor of P over Q, that is plus or minus 1. If you substitute 1 and minus 1, is it possible for this polynomial to be equal with 0? If, for example, if you evaluate at 1, simply add these coefficients. 3 minus 11 plus 8 plus 4. 3 plus 8 is 11. 11 plus 4 is 15. 15 minus 11 is 4. So 1 is not a 0. If you make minus 3, this is minus 3, minus 8, minus 11, plus 4. Still, this is not 0. So let us consider the next factor, plus or minus 1 over 3. When x is equal to minus 1 over 3, f of minus 1 over 3 is equal to minus 1 over 3 cube, minus 1 over 27. Minus 1 over 27 times 3, minus 1 over 9. Then minus 1 over 3, the whole square is 1 over 9. It is minus 11 over 9. Then 8 times minus 1 over 3, minus 8 over 3, plus 4. Now simplify this number. Because the denominator of this is 3, multiply this by 3 times 3. It is negative 24, negative 35, negative 36. Negative 36 over 9 plus 4. Negative 36 over 9 is minus 4. Minus 4 plus 4 is equal to 0. So the first zero of this polynomial is obtained, and it is x is equal to minus 1 over 3. Then when x is equal to 2, f of 2 is equal to 3 times 2 cube minus 11 times 2 square plus 8 times 2 plus 4. This is 2 cube is 8, it is 24. 2 square is 4, 4 times minus 11 is minus 44. 8 times 2 is 16. 16 plus 4, 20. 20 plus 24, 44. 44 minus 44 equal to 0. But if you continue evaluating this polynomial, you cannot find another 0 different from 2 and 1 over 3. Because as you can see, f of x in factorized form is 3x minus 1 times x minus 2 the whole square. So 3x minus 1 times x minus 2 the whole square means this 0, the second 0 of the polynomial, repeats itself as a zero of the polynomial twice. The maximum number of possible zeros of the polynomial, this given polynomial is 3, because its degree is 3. So the maximum possibility is 3, but if there is to repeat itself, then the number of zeros is f of x. So the only zeros of f are 2 and 1 over 3. The second example is 2x cubed plus x squared minus 4x minus 3. Again, for this polynomial, all of its coefficients are integers. Then list the factors of p, that is 3, and the factors of q, which is 2. Then we list the factors of p over q. The factors of p, that is 3, are plus or minus 1 and plus or minus 3. The factors of q, which is in this case 2, are plus or minus 1 and plus or minus 2. Now the factors of p over q. Make the factors of p numerator and the factors of q denominator, and place the plus or minus sign before these factors. So 1 over 1 is 1, so plus or minus 1. 1 over 2 plus or minus 1 over 2. Then we consider the next factors of p, or we list the factors of p over q, whose numerator is 3. So 3 over 1 is 3, plus or minus 3. 3 over 2 plus, the different factors of p over q are 1, 2, 3, 4, 8. So if this polynomial has any rational zero, it must be from among these 8 numbers. There is no other rational number which can make this polynomial p equal to, this polynomial f equal to 0. Now, evaluate this polynomial f at x is equal to 1 and minus 1, because in any factors of p over q, the simplest numbers are plus or minus 1. Now, when x is equal to minus 1, f of minus 1 is 2 times, this is positive 1, this is positive 4, and then the first zero of this polynomial, and it is minus. When x is equal to 3 over 2, f of 3 over 2 is equal to 0, but f of x in factorized form means it is equal to 2x plus 1 the whole square. So one of it is 0, repeats. So the multiplicity of minus 1 is 2, and we have another 0 that is 3 over 2. So the maximum possible number of zeros for this polynomial is 3, because its degree is 3. So we stop at this stage, and we take minus 1 and 3 over 2 as the only zeros of this polynomial. Now, it is time for you to try these 2 questions. The first one is, which of the following is not a rational zero of the polynomial f of x is equal to 8x cubed minus 2x squared minus 7x plus 3? And the second one is, between which of the following consecutive integers does the polynomial f of x have its irrational zero? So please try these questions. ትንሽ ይቀረኛል። ቀጥሉ እናንተ እስከዚህ። ሮብሰን እየሰራችሁ ነው? እሺ ኦኬ የሚመልስ የለም? Okay, the question is, which of the following numbers, 1/2, -1, -2, 3/4, does not make this polynomial equal to 0?
You simply substitute 1 over 2 minus 1 minus 2, 3 over 4 in place of x in this polynomial and simplify. So which number does not make this polynomial equal to 0?
-2.
The answer is C. Yes, -2. 1 over 2 minus 1 and 3 over 4 are all the zeros of this polynomial. Okay, between the following negative integers does the polynomial fx of it is irrational 0? Because between these integers, if f of x is positive and at x, which is the other value, it is positive, then the consecutive integers will be, they will be taken as by the location theorem where there is one irrational 0. So check and determine between which of the following consecutive integers does the polynomial have its irrational 0.
ሚስተር መሞከር ይቻላል? መሞከር ይቻላል?
ፕሮፌሰር
መልሱ ዲ ነው።
ትክክል ነው። ኤክሰለንት። A and C. This polynomial changes its sign between -3 and -2 and between 0 and 1. I don't think there is no sign change as we evaluate f of x between -2 and -1. Therefore, the only irrational zeros of this polynomial are even between -3 and -2 and 0 and 1. So the correct answer is D. So this is all I have for today. We'll see you on Monday with a different topic, or maybe if you need, I will add more examples on this. Thank you for watching.